Hello everyone, welcome to Royal Palace online classes. Today this is the last topic of your moving charges and magnetism. So let us discuss a loop as a dipole. See, a current carrying loop acts like a magnetic dipole. You can observe here, if you consider a loop, this current carrying loop which is carrying current I acts like a magnetic dipole. So in order to understand this clearly, you should know about electric dipole. Electric dipole consists of two equal and opposite charges of charge q separated by a distance 2a, and dipole moment is equal to P is equal to one of the charges into distance between them. This is the dipole moment. It is a vector quantity and its direction is from negative charge to positive charge. So that's what you have studied. And electric field on the axial line of the dipole is 1 by 4 pi epsilon naught 2p by r cube or x cube. For a short dipole, you can go back to your previous chapter and you can see this formula. For long dipole there is another formula. After approximation you will get this formula. Okay. So here P stands for dipole moment. Similarly, we can take the formula of axial line of the circular coil. Formula of axial line of the circular coil at a distance r. What is the formula? B is equal to mu naught Ni r square by 2 into x square plus r square whole power 3 by 2. This is the formula. This we have derived in our previous videos. You can just refer back. Now I will take that formula and I will show that this loop acts like a dipole. I will take the formula and I will show that this loop acts like a dipole. So take B is equal to B on axial line or BA is equal to mu naught Ni r square by 2 into x square plus r square whole power 3 by 2. This is the formula. Now this I will divide and multiply with 4 pi. Multiply and divide with 4 pi. Now what happens? Or you can take 2 pi also. Let us multiply with 2 pi. Divide and multiply with 2 pi. So what you will get? B axial is equal to mu naught Ni 2 pi r square by 4 pi into x square plus r square whole power 3 by 2. If r is very much less than x, that means there is a short loop, very small loop. If r is very much less than x, what you can write? This is equal to mu naught Ni 2 pi r square divided by 4 pi x square plus r square. I will nearly take it as x square. So this will become x square whole power 3 by 2. 2 and 2 will get cancelled. It will become x cube. So this is equal to mu naught by 4 pi into this. I will write I into n into pi r square is the area of the loop. So n into 2a by x cube. Again upon simplification you will get mu naught by 4 pi 2 into Nia by x cube. Now just compare these two formulas. This is the axial line of a dipole electric field according to person called Coulomb we have derived. Same thing according to Biot-Savart, we derived this formula, that just I made some mathematical calculation, just multiplied and divided by 2 pi. You can observe exactly at this point what is there. In place of P, you are having NIA, therefore magnetic dipole moment M is equal to NIA. And a current carrying loop acts like a magnetic dipole. A current carrying loop acts like a magnetic dipole. And if the current carrying loop carries current in anti-clockwise direction, the current carrying loop carries current in anti-clockwise direction like this, anti-clockwise direction, then what you are seeing is north pole. What you are seeing is north pole. That means this loop is present on the board, you are seeing, your face is seeing north pole, other side you are having south pole. So a loop in on the plane of the board acts like a magnet like this. It is acting like a dipole. One is north, other one is south. So what you are seeing is north. When current is in anti-clockwise direction, you can remember like this. You can remember like this. This is the direction. So when there is a loop carrying current in anti-clockwise direction, your face is towards north, other side you are having south. This is north, this will be south. You can observe here. It acts like a dipole. And next, if it is carrying current in clockwise direction, what you are seeing is south. So how you got this direction? It is not theoretical. We can prove this, how you are seeing north pole. See, loop is present on the board. You take a small part of it you take. This is the current direction, okay, and you hold this wire such that the small part you hold such that thumb is pointing towards the direction of current, and see the curled fingers will give the direction of magnetic field, means magnetic field is towards you, and magnetic field lines emerge from north, enter into south. What role positive charge plays in electrostatics? Same role is done by north pole here. North pole is nearly equivalent, means analogous to positive charge. So what positive charge? The path followed by a positive charge in electricity, we call it as electric field. The path followed by a north pole, we call it as magnetic field. Magnetic field is always in the direction of force experienced by north pole. So force is coming in this direction, that means electric field lines should come from north to south. That means what you are seeing is south, backside north is there. So this is the direction of magnetic field lines. Magnetic field lines are coming out. Magnetic field lines are coming out means, suppose this is magnetic field line, it is coming out towards you. That means it is coming towards south. That means what you are seeing is south, backside what is there is north. So this is the explanation. Same for north also you can get. And this current carrying loop acts like a dipole, and there is one difference between the dipole of electricity and dipole of magnetism, that we will again study in magnetism and matter. The difference is isolated poles are not possible in magnetism. Isolated poles are not possible, whereas isolated charge is possible in electrostatics. In electricity, isolated positive charge is possible, but in magnetism, isolated poles never exist. You take small part of the atom, if you take very small part of the atom, it will have both north pole and south pole. So it will never exist. That's why magnetic field lines are closed loops. So this is the explanation, and we can prove that a current carrying loop acts like a magnetic dipole. Okay. Now next let us discuss the magnetic moment of revolving electron. Let us discuss the magnetic moment of revolving electron. Let us consider an electron is revolving around nucleus at a distance r, radius r. Magnetic moment of that revolving electron is equal to NIA. Then that is equal to I into A, that is E by T into pi r square. Current is equal to E by T. Charge by time period is current. Then E by T into pi r square, area is pi r square. Now time period is equal to distance travelled by velocity. Time period is distance travelled by velocity. Then calculate magnetic moment. Magnetic moment is equal to E by T, E by 2 pi r by V into pi r square, that is E V into pi r square by 2 pi r. Pi and pi will get cancelled. Then r square and r will get cancelled. This is equal to E V r by 2. This is sometimes represented by m, and in your textbook he has represented with mu. Now what you do, this E V r by 2 you can multiply and divide with mass. Multiply and divide with mass. Then what you will get? This is E V r m by 2m. Then mvr is called angular momentum. mvr is called angular momentum, that is equal to E into L, where L is the formula for angular momentum, symbol for angular momentum, by 2m. This is equal to mu, magnetic moment, or you can write it as capital M. You can write it as capital M also. Then mu by L is called, mu by L is equal to E by 2m. This is called gyrometric ratio. This is called gyrometric ratio. Gyrometric ratio. Magnetic moment by angular, that is angular momentum, MVR, we call it as gyrometric ratio. And according to Bohr, angular momentum is equal to NH by 2 pi. NH by 2 pi. So same formula you substitute, magnetic moment is equal to E into NH by 2 pi, NH by 2 pi into 2m. This L value I am writing here. This L value I am writing it as NH by 2 pi according to Bohr's model. According to Bohr's model. So this is how much you will get? NEH by 4 pi m, and this m is mass of electron. This is NH into E by 4 pi me. This is equal to mu. Okay. This is the magnetic moment of revolving electron. Sometimes it is also called Bohr magneton. Okay. This is the condition. So with this we have successfully completed a chapter called moving charges and magnetism. Some next class we have to do problems based on moving charges and magnetism. So you can just go through all the videos and just make a list of the formulas so that we can complete our problems in the next session. Thank you everyone for joining me. If you have any comments, you can leave in the comment section.